Thank you very much for the invitation and thank you for the kind introduction. Today I've tried to do a play on words with the fact that we'll be talking about oxygen redox in lithium-ion batteries and related sodium-ion batteries, and I've called the title the whole picture linked to the ligand whole picture. And one of the things I try to do with slides is show on the first slide essentially the key result. And essentially what I'll be talking about is using very fancy techniques like resonant photoemission spectroscopy to simply look at where the electrons that we use as our current in electric vehicles coming from our battery materials originates from with orbital sensitivity. So in this way, we can look, for instance, at lithium nickel oxide. As we charge up, we delithiate, we extract electrons to essentially charge up our battery. And the idea is, where orbitally are these electrons coming from? Can we use direct probes of electronic structure to link it back to the originating orbitals? This helps guide computational studies, but it becomes really important when it comes to terminology when we are addressing what do we mean by next generation battery cathodes. So the idea of this talk is why this is important, how we are trying to address this in terms of what do we mean by not just oxygen redox, but what do we mean by nickel and cobalt redox, and why is this important in terms of developing new types of materials, and does this present new ways of coming up with solutions? So I tried to do a bit of an infographic with regards to a recent paper that we've just got out, more information at the end, but essentially the idea is when we're taught quite early on with regards to battery redox, we kind of link that to the view that we are doing changes in electron counts with d shells. It's basically the d orbitals, which are the electrons we care about. And essentially, if we're doing like ion 2 plus to 3 plus, we can link that very neatly to going from 3d6 to 3d5 with regards to electron counting. The same argument should be made really with lithium nickel oxide, in the sense that you would imagine that you're just changing your d electron count, and that would mean that your starting point should be Yan teller active material, if you're familiar with sort of those sort of terminologies. But essentially what we point to is you start seeing, even though you are doing nickel 3 plus to nickel 4 plus, you are having a significant contribution of your orbital electron density comes from those which have more oxygen 2p character. And this is really important with regards to explaining their behaviors, but also it's providing the groundwork of linking that terminology with how other oxide electronic structure systems exist. So what we'll be showing is how to reconcile the late transition metal oxides with regards to condensed matter physics terminology that's used to describe things like high temperature cuprate superconductors, where they've had to develop the correct terminology to deal with the fact that we are moving to systems where there is a high degree of correlated phenomena and hybridization, etc. So I saw on LinkedIn Professor Alamgir. So I've known Faisal for a long time. We have shared links to Brookhaven National Labs. And I remember seeing on his LinkedIn post promoting today, his highlighting back that this is a long-standing problem. And he's right. So I've highlighted one of his papers, which is essentially one here where he's looking at lithium nickel oxide as a mixture of a third each of nickel, manganese, and cobalt. And highlighted from the abstract the key bits there, where it's found that as they pulled out only about half of the lithium, most of the redox was seen in this case using hard X-ray absorption spectroscopy, nickel oxidation, and then the second half seemed to suggest it was more accompanied by transition metal oxidation. And so what I want to do is kind of build on this, kind of show the direct measurement techniques that we've been doing to examine this problem, link it into the context of oxygen redox materials, where essentially the argument is that you can have more capacity from having the oxygen more active. And what we'll do is at some point it will reconcile back to essentially this sort of these sort of conclusions and what we can say. I've been toying with whether to include this slide or not, and I see that it's recorded, so I thought it would be a good idea to just put here as kind of something to refer back to. But the reason why we are quite interested in oxygen redox is essentially the opportunity to increase capacity. And one of the techniques that has been used very strongly is known as resonant inelastic X-ray scattering. This is basically where you do the absorption, which is essentially like the techniques that we're using here, and I'll explain more going forward. But essentially, you measure the recombination in the emission process. And it was my start point with some of this work links back to when we worked with Wanli Yang at the Advanced Light Source to help with regards to developing a higher efficiency spectrometer at the synchrotron facility in order to essentially map the electronic structure with essentially RIC. So if those are familiar, those with a photoemission, you might be aware of angle resolved photoemission. There's kind of like a bulk orbital selective ARPES capability. This was designed to help address some of the issues with characterization of things like manganese L-edge, where you have self-absorption effects, and it gave the ability to distinguish some exotic redox states like manganese 1+ oxidation state. But it was really this technique started to show features that seem to only appear in the cases where we could assign it to oxygen redox. So I want to just talk about this a bit more. But essentially, the long and short of this technique was essentially that it is a very good sign of O2 molecules in the system. So I'm going to start this presentation a bit like a series of stories. So in the first one, it'll be a scientist is basically saying, well, old battery cathodes get electrons from the metal ions. New cathodes should also get more capacity, but from oxygen playing a role too. And the reason why I care about this is energy density is the key factor for essentially electric vehicles, because when you do physics undergraduate, you're taught how to consider a rocket ship, and you've got to consider the fact that your fuel is expelled, etc. With a car, it's purely a work done consideration. You don't have to do a differential equation like you do with a rocket ship, because you're carrying your fuel the whole time. Your battery weight is essentially very similar, is the same when it's charged and discharged. And essentially that means that your energy density of your pack is the key parameter. So we have both energy density with respect to kilogram, and also energy density with respect to liters of volume, because you've got a fixed size you can fit into, and you don't, and to increase your range, you have to improve your energy density in this case with watt hours per kilo. So that becomes a really important unit. And if you look at the types of chemistry that you can have with that, essentially means that for the range you're interested, lead acid chemistries do not give enough energy density. And that's where things started to open up with lithium ion, because at the cell level, you were able to achieve nowadays around 300 watt hours per kilogram. And it's important to remember that the cell is not the same as a battery pack. When we talk about batteries, we often talk about packs. So you've also got the component of improving your cell to pack ratio has also been a way in which automobiles have improved range, etc. But if we look at the chemistry side, we're really interested in increasing our energy density, which means we need to increase our capacity. So if we sort of look at the ways in which we look at classical lithium-ion batteries, we can consider the source of our capacity in a real battery is a cathode material, the positive component, where we kind of link lithium metal oxide, in the case of lithium cobalt oxide, with a counter electrode anode of graphite. If we consider the cathodes, because that's the source of our lithium, the idea is we want to increase how much lithium we're extracting. Lithium ions and the corresponding electrons is what we care about for our current. if we can pull more lithium in and out reversibly, that's a way to increase our capacity. So let's start with a classical layered system like lithium cobalt oxide. In that case, we have a layer of transition metals like cobalt coordinated with oxygen as a slab with lithium ions as spaces between those slabs. If you consider them CS, so you have your A, B, C stacking. And if we combine Faraday's laws of electrolysis, we can come up with a quick equation to determine, based on the mass charge ratios between a case where we have the fully lithiated and the fully delithiated case where we pulled out all the lithium, you can actually determine what our theoretical capacity is, around 274 milliamp hours per gram. And to be honest, when we compare lithium cobalt oxide or changing the ratio of nickel, cobalt, and manganese, essentially very similar numbers for your theoretical, because they have very similar atomic masses. But one of the key components is with lithium cobalt oxide, with first commercial adoption, we were only pulling around 50% of the lithium. We've been increasing the amount of nickel to substitute for cobalt for various reasons, but for the same voltage point, we can increase the amount of accessible lithium to something more like 2/3. The other approach, so in those classical systems, classical layer systems, the thought process is to compensate for the lithium ion and the electrons coming out. You're going to have a change of oxidation state from, say, cobalt 3+ to cobalt 4+, nickel 3+ to nickel 4+, etc. So the view is the transition metal is the active component of the redox. In the case where you've got lithium excess systems, this is where we can increase the number of available lithium. So the way to look at this is not just having the same structure where you have the slabs of metal oxides in between layers of lithium ions, you also have lithium in that transition metal slab. And that means now we have two sites where we're pulling lithium from. And with the stoichiometry, it allows us to do 2 lithium per unit formula. The interesting component in this is your manganese is now going to be in the 4+ oxidation state. And it generally does not like to go to higher oxidation state without changing from octahedral to tetrahedral. So we usually find there's a strong tendency for it to want to not go higher in metal oxidation state, but we still see very high capacity in some cases, and that led to the view that this is now the oxygen being the redox active component. Then we have essentially these composite materials, which are like these nanoscale composites, not quite a solid solution, where we have a mixture where you can kind of have different ratios of those two end members to kind of have a single notation where we have a lithium excess system. And the view here is that you can have, like, typically with a lot of the materials that have been developed as these, if they're excess, they usually have about 1.1 to 1.3 lithium per unit formula. It does increase your theoretical capacity, and the view is now you have both metal and oxygen as your redox active components. So the view is that oxygen redox is a way that we could probably get more capacity, but the actual mechanism underlying it has been debated a lot in industry, in the community. So there's been various views on this, and this is kind of linked to what I mentioned with different techniques to look at the oxygen environment. And this was a review we did a few years ago. Myself, Claire Grace, Dan Weddingham, Anton Landerdien, and Shelley Meng, with regards to considering all the different candidates. And so there's various papers that are coming out talking about novel metal oxidation, where there's migration, oxidation migration, and etc. Whether this was associated with the ability to do something more like a lithium air-like consideration, where essentially you form O2 molecules or peroxides, to whether we kind of view it as actually associated with rehybridization between the metal and the oxygen, with moving away from purely ionic like bonding, and to, is this actually where we got a localized electron hole like you would have in semiconductors where we can type materials. So the idea is, if we go to that, if we look at that statement, old cathodes will get electrons from the ions and also from the oxygen too. One of the things a good scientist should always know is that true? Can we verify it? So let's do a direct example. Let's take a lithium excess case. That's that composite. And you see the voltage profile has two main parts. It's got a traditional charge up process that you would expect for essentially a layered oxide, a classical layered oxide, and then it's got this plateau region which looks very distinctly different. And the view with that was, okay, well, this is where you've got essentially your metal redox, and this is where you've got your oxygen redox, because it's reflecting the different components, and you're doing the oxygen redox first and then the metal redox afterwards. And this ratio of plateau would depend on what ratio of stoichiometry you had, which would follow the argument that I'm increasing the amount of Li2 MnO3, I'm now seeing more oxygen redox, I'm seeing a longer plateau. If you do ZANES, which is X-ray absorption spectroscopy, this is the thing that I showed from Faisal's paper earlier. The argument with this is that if I look at the absorption between the metal 1s orbital to the unoccupied available states, we can use this as essentially a way to monitor oxidation states. So this edge shift this onset of absorption will shift as you go to higher oxidation states. It will shift to higher energy. So what you see with this is initially there's a shift in that first region, and then it starts to plateau off. And the same with the cobalt. Manganese is a little bit more complicated. There's a bit of restructuring, not necessarily associated with the redox. But the rule of thumb is, I'm now going to this regime where I said there would be oxygen redox. I'm no longer seeing metal oxidation shifts. This is what you see on the first charge. And this is really important because in real batteries, the first few charges you have of cathode materials, you don't really see because that's part of a formation process to prepare the SEI on the graphite. So in academic studies, you might focus on the first cycle, but in industry, the first cycle is where we'd expect to have changes associated with preparing it for longevity. So if you look at subsequent cycles, what you would see is actually that voltage curve would actually, on the second charge, become more of a solid solution. You'd lose that first plateau. The argument is you're doing some sort of activation of the oxygen redox in that first cycle. One other way you can think about it is that where the lithium is in that transition metal slab follows this honeycomb structure as a superlattice. You can actually see an XRD right from the start. And that's because if you, instead of looking front on like we were, but look top down with those metal slabs with the lithium, you would see this honeycomb structure, which is lost upon the first charge. But you can recover it, as work with Shirley Meng and myself and others did in this work. You can actually recover it by heating. So you can cycle your battery, you can lose that plateau, but you can reheat it to reform your honeycomb structure. So that's not necessarily an indicator, that plateau, that you have oxygen redox. It just indicates the type of structure you have. So this might account for why you see differences between different types of polymorphs of lithium excess. Sometimes they point to that they have strong oxygen redox because they have a strong plateau that resists. But that largely comes down to whether it's a case where the microstructure is one where the honeycomb-like structure is present and lost or not. But the next component, as I mentioned, oxygen K-edge RIPS, and you can kind of think of it as doing the absorption component and emission component of the oxygen K-edge. So instead of doing nickel edges where you have to use harder X-rays, use softer X-rays, and we can access the oxygen region. And what we found with using that RIC spectrometer very quickly after it was implemented, you could see in this example here of taking that same material, and as you charge up, essentially this are essentially maps of the electronic structure. You can see an elastic peak associated with exciting and associated with the elastic peak associated with exciting the X-rays and having no loss. what we started to see was an additional feature, which is circled here, which you only see once you start going into those high voltages where your transition metal appeared to stop doing redox. Now you start seeing a new feature. So it was like, this shows correlation. We see this feature in the oxygen spectra that looks different to when we're not in where we view them the oxygen redox. So this correlation between this feature suggests that we're in a region where there's oxygen redox. So this is kind of where a lot of the field are with this. The idea is that we have a distinct difference between the transition metal redox region and the oxygen redox region. So why don't we look at our model system endpoint of Li2MnO3? So that's a lithium excess system where we've gone to the endpoint. That's like putting 100% in a composite structure. And what we found is that system does not show any evidence of that oxygen feature, oxygen in RIX. The majority of why we see capacity associated with this material system is actually because it's decomposing very heavily. When you read the literature on Li2MnO3, there's a lot of talk of activating Li2MnO, this material, and essentially that means making it very small particles. So you increase your surface area. This was nice work with Brian McCloskey, where essentially he showed that we could count for all of the capacity in the first cycle, hundreds of milliamp hours per gram, essentially just because we have a 4-electron process where we're seeing how the material is decomposing, and because we're decomposing, we're freeing up electrons. And because we're decomposing, we could actually see that in the zanes of the magnesium, where when we charged up, it actually reduced. And that meant on subsequent cycles, you're going on a 3+ to 4+ conventional redox after you've done that first cycle. But you only see noticeable amounts when you kind of got a large ratio between your surface region and your bulk. So small particles, you see this; larger particles, you don't see this. So this was work where we said, well, we wanted to understand more of those mechanisms. Let's use our model system of the endpoint, and then we realized the endpoint was not actually a good candidate for describing oxygen redox. So we went, okay, well, if the oxygen redox endpoint doesn't show oxidized oxygen RIX, what about? But one of the things we found very early on, in fact, one of the first measurements on that spectrometer showed us, and it took us about 4 years to sort of try and present an argument as to why we thought this was occurring, was essentially if we take our conventional layered oxides, we compared LCO, lithium cobalt oxide all the way to very high nickel layered oxides, different ratios, lithium cobalt with aluminum, lithium nickel with aluminum instead of manganese, etc. And what we found was we always see these these features, the same features, this same loss feature here, corresponding to an enhancement of elastic peaking. So this is kind of showing us on resonance. We always see this feature at the same energy when we're in the charge state, and then we lose it in the discharge state. And this had been fingerprinted as essentially a sign that you have O2 molecules in your system. And what we found with this is when you go to very high voltages, you would see it in all of the layered systems. You would have to go to high states of delithiation. So it's not just voltage, it would be, if you compare it the same amount of delithiation, it was always when we were in delithiation regimes above 70%, you'd start seeing it. And the argument then is like, well, this allows us to have a model system, yeah? Because is it just because we're seeing more oxygen redox at high voltages and we're only just going into the high voltages here? Is it a case where we're starting to see this onset? Can we use this as a model system to better understand what do we mean by oxygen redox? So let's take a model system. So we took a commercial. So one of the things that was mentioned in the introduction is I like taking real format cells and doing operando, but I essentially like doing sort of more academic level interrogation of materials in real format. So we basically took some industrial, commercially available single crystals of NMC811, made it into a full pouch cell. This is how it looks when you charge it up. We can take it to high states of delithiation. We could extract out both electrodes prepared to kind of show that everything behaves as we've seen before with other systems. We also did operando, where we did the pouch cells and looked at the Zanes at the same time. And they both showed in that work that, yes, once you get to these high states, you see the nickel stops appearing to shift on the Zane, so it seems to appear to stop oxidizing. The same with the cobalt. And then we did XFs at the same time. And the nice thing about XFs is you start looking at all the scattering processes associated with the tailing of these. So you look for hundreds of EV. You essentially turn it into energy space and then turn that into do a Fourier transform, and that allows you to be very sensitive to the coordination structure. First, the first transition metal to oxygen bond length, and the next transition to metal to transition metal. So we could actually monitor that as we delithiate, after we still pulling out electron capacity in a full cell. We see that both the nickel and the cobalt bond lengths for all the different systems would shrink, which is what you expect when they're oxidizing, but then plateau out afterwards. And this was quite interesting. We kind of viewed it as this would be in a region where there's a lot of interest, because this is a regime of where we try to avoid in real cells, because that's where we see a lot of degradation. And that's where we did the high resolution rigs. So in this case, we're not doing those maps anymore. We're doing really high resolution, because we see that spot where, if we look in that, in those maps, we're now doing a slice across this at high resolution. So we're going to see this elastic peak. We're going to see some features down here, and we're going to see this feature pop up. So we're doing like this. In this case, we're doing literally this slice as a function of different points which we've characterized. And what we found there is, yes, when we can see the same features very brightly using rigs, high resolution rigs. We can see essentially the emergence of that peak as we go to the highest states of delithiation, and we can see these vibronic states, which are the way these spacings between them are how you tell it's trapped O2. So this would suggest that we're doing like something similar, like what's happening in lithium excess systems, we're doing in our layered systems, and we're seeing essentially about the same thing. So we kind of viewed it to a first approximation. We're seeing nickel oxidation up to about 4.2 volts, and we're seeing clear signs of this oxygen signature above 4.2. And we know with these systems in nickel rich, they like to evolve gas. So the idea is that because we're starting to see trapped oxygen because we've got gas evolution, and would that help explain why we have gas evolution? So we did DEMS or OMS, operando mass spectroscopy, and what we found was the onset of where we see the gas evolution, we were seeing Rig signal below that. In fact, if you look very carefully, we were able to see the Rig's spectrum in our pristine material. That would suggest there was some O2 right at the start. The other argument was you have more oxygen redox in lithium excess systems. You would expect there to be less in the layered systems, but honestly, we were seeing the same amount. The other argument was, oh, well, in the case of high nickel content materials, you're going to have a lot of propensity for intermixing between nickel and lithium. So that's why we did lithium cobalt oxide. For those not familiar, lithium cobalt oxide is a great material because it really keeps the lithium in the right places. The cobalt does not like moving around, whereas in the nickel rich cases, nickel 2+ and lithium plus like to move around. And what we found is we saw the same intensity regardless of which system. And we saw the fact that there was actually the same species because we had this high resolution data allowing us to see the spacing. So we've done quite a bit of work of looking at that, and it's basically one where we were saying there's obviously an electrochemical reason as to why we're seeing this feature. And there's some nice work by Jean-Marie Tarascon's group that pointed out that similarly, there didn't seem to be an when you study across all the different, so there's a huge library of different cathodes. Essentially, it was one where you can readily see this feature in all of them. They're pointing to the fact that this is likely associated with a defect. So we went a bit further in our study because we had these nice model system to look at this further. So what we did was we said, Well, if it's forming trapped O2, it's probably the argument at the time was essentially to form like these little voids associated with so nanoscale voids that are here about 7 angstroms, where there would be an O2 molecule trapped in your structure. So the idea with this is you can use scattering to observe things that are not there because of the way in which the voids would scatter with the X-rays. So this is an example of small angle X-ray scattering. And essentially, this was nice work by Shirley Meng and Karina Chapman, where they essentially took these lithium excess systems and said, you know what, we use SACs to see if we can see these voids form. And we do see these voids form. We see this bump here as we cycle. It does vary. And we can see evidence that we have these voids. And we don't see these in conventional layered oxides. But it does, so we do see them in the lithium excess system. It seems to be something we do see. But they pointed to the fact, and this was ex situ studies. So what we did is we took the pouch cells of our layered oxide, E811, and these are measurements every 2 minutes as we cycle up and down. And essentially we don't see this bump. We don't really see this bump. This is within the noise level. And we stressed it. We took it to quite a large window of operation. We cycled it aggressively for hundreds of cycles, and we did not see any evolution. So what we're saying is we're seeing the RIC signal, but we're not seeing the corresponding number of void states where those trapped oxygen could be is below a detection limit. So that would be consistent with it being a defect, whether that's induced by the beam or whether it's associated with the growth. And that's where we were pointing to the fact that if we look at lithium nickel oxide as our example, as an endpoint, essentially it's unstable with respect to thermodynamically unstable with respect to nickel oxide and O2. That doesn't mean it spontaneously spontaneously changes into those products, because essentially when oxygen is lost, the oxygen vacancies move incredibly slowly, like they operate moving in the period of like days, months, years, where most of your chemistry is done at attosecond, femtosecond level. So essentially, this means that you do see this reaction that happen quite a bit, but you usually see it more as formation of a surface crust of NiO, what's known as a rock salt layer, up the top of on your material, where essentially that can act as a trap for your lithium going in and out and causing problems. So it is a problem, but essentially you do see rock salt formation with O2 generally associated. So that gas evolution we see is that I pointed to here. That's why we usually don't go to such high voltages, such high delithiation in commercial cells, because then we can form oxygen loss. That's bad for safety purposes, and we start having issues to do with the fact that we start having these structural transformations at the surface. But that same argument with regards to that instability also means that when you're doing synthesis, there is a tendency for it to form. There is an argument where, from DFT calculations, you find what energy states are favorable, and you do find certain types of defects where you have this configuration of a nanopore with a trapped O2 molecule is actually one of the sort of more favorable states at the defect level. And so that would also rectify with the view that we do see essentially evidence of these O2 molecules right from the start. It can be associated with not just beam-induced damage, but also whether you have the defects associated with the material. So, part 2, we've got to the bit where we said it should be metal redox, oxygen redox, and essentially we're now questioning the oxygen redox. So part 2 is essentially Yoda saying, no, different, only different in your mind. You must unlearn what you have learned, and I'm very careful not to do the voice with the recording. So that made us revisit lithium nickel O2 as an endpoint model system, because in that case, we would see the same RIC structure, those signatures from the oxygen K edge, And that meant we started to look at different levels of DFT calculations. So there's very nice work from Annalena Grenier, in collaboration with Claire Grauer, myself, and others. We kind of, the work was essentially focused on understanding if we do different levels of calculation. So you have DFT with different functionals, all the way up to DMFT, dynamical mean filtering, which is kind of above DFT. Could we monitor by looking at both the endpoint? So we're not talking about how it charges up, we're just looking at the endpoint, and then examining the electron density on your nickel and your oxygen. So that's where you got ionic charge on your oxygen and your nickel. And what we found is there's variations with which level. So if you can go at NIO, use different levels of code, different levels of sophistication on the model. You do see variances, but essentially all of them agree that as you go from NiO, lithium nickel oxide, to NiO2, there is a tendency that more of your change of electron density, where your electrons are being abstracted from, spatially come from regions which are more closer to the nickel ion than closer to the oxygen ion than the nickel ion. And so the nice thing about this is from those calculations, we were able to actually pull out data from the experiments and compare that with what the simulated absorption edges, both the K edge on the nickel and the oxygen should look like. And what we could do is relate all of the changes that we observed in essentially changing the bond lengths, the first coordination shape. And this becomes quite important for describing some things. So the idea is that this would suggest, yes, during this process, as I go from nickel 2+, 3+, 4+, most of the changes on my electron density are more on my oxygen than my nickel. And it starts even before lithium nickel oxide. And I've now got a way in which I can link these calculations to experiments. So, and none of this requires trapped O2 to explain any of the capacity or any of the line chains except for the signature of the O2. And we're saying for the case of lithium nickel oxide, this is likely a defect at a defect level, not associated with capacity. So when we published this, a good collaborator of mine, Russell Egdahl at Oxford, now retired, but an excellent solid-state chemist, kindly wrote on Twitter at the time, which was fashionable with academic Twitter. It was definitely Twitter then. I thought this was well established in the 90s with the high temperature supergrades that you would have is essentially oxygen holes. So it's really nice data, but hardly unsurprising. And that's what you love to hear whenever you put out your good work, but it did prompt me to answer this question more generally. I'm going to just point to two things. So this component with the bond lengths links to an important component, and I'll do that first. And then we'll address the fact that what would Shorski say with regards to this system? How can we rectify the view that we were still kind of thinking, what is the best terminology to describe this? Is this actually the right conventional notation? And it links back to what do we mean by metal redox versus ultra redox? So one of the things we wanted to point to and kind of link to what I pointed to with Faisal's work is when we first looked at this, we could see that the electrochemical profiles are very different between lithium rich and lithium excess. So as I delithiate, I'm pulling out, I'm going to have a profile which is a solid solution, and then I have a solid solution and a two-phase profile here with the lithium excess. So this is nice work we did a while ago to try and investigate whether there was any possible manganese 7+ and evaluate the effects of beam damage, etc. So this was some work that we kind of had in supplementary. But these were model systems. We took a layered system 442 and our lithium excesses. So this is where we break it up into the region where we previously would say the Zanes would show metal is doing stuff here, and then behind here we'd say the oxygen redox, and we'd kind of said we saw similarities here. For a long time we were focusing that primarily on how the C lattice collapsed, because we knew that this was a region where we'd start seeing some interesting behavior with layered oxides, and we were trying to understand the degradation in that. But if you look at that C lattice, there's no rhyme or reason to view it as there's any reason why they would behave in a similar way. And the C lattice is one where is actually a good probe of this. If we go back a step with regards to the simulations, we want more that first coordination shell. And in that case, it's actually the A lattice, which is a better proxy for it. And what you can see is, remember I talked about how the bond lengths of the XFs start to plateau out? It's reflecting how the A lattice is plateauing out. And that shift that we see with the Zanes in the metal cases here is essentially that short bond length. So when that plateaus out, that's where you no longer see evidence of transition metal redox happening, is just because those bond lengths have stopped moving. So I get to the punch of it. So the next bit was to say, well, okay, let's reevaluate it. Is it fair to say that it's different notation that we need to use? Should we use 2 plus to 4 plus? Should we talk about oxygen 2 minus, 2 minus, or some mixed one? And unfortunately, that the person associated with that tweet mostly published some work about negative charge transfer energy compounds in correlated systems, and essentially had done loads of calculations looking at different metal oxides and sulfides. And what he kind of showed was a lot of math, and for the sake of simplicity, it really comes down to whether your metals or your topmost state metal d orbitals are topmost states, or whether you have more contribution from your oxygen bands to topmost states. And you kind of can view it as your oxygen band stays at a fixed level with regards to the vacuum level, and you're changing the population and energy levels of your d orbitals. So there is a propensity for a case to go from positive to negative charge transfer, where essentially with your ionic case, you're going to have most of your the topmost states will be a d orbital, and as you go from 2 plus ion to 3 plus ion, you're going to stay in that charge transfer, which is positive, which indicates you've got an ionic system. If we look at the nickel and the cobalt, you'll see that between 3 plus and 4 plus, you're in the negative regime, where instead of most of the changes being associated with states, topmost states being of d orbital character, they are more of oxygen character. And so we tried to show this more schematically as to, if I looked at electronic energy diagrams, I'd imagine in my ionic picture, my oxygen 2p's here, now I've got my unoccupied d orbitals, and as I depopulate this, we increase the unoccupied states in this way. And then if we go to the case where we go to late transition metal oxides or high oxidation states, then we have more of this mixing where we have increasingly more oxygen character on the top of the states, and the notation would that be reflecting this hybridization and this type of character state would be the formation of ligand. So the idea is that we should see this, and then that led to the question of how do we directly see this? And this is where I linked it with photoemission, because that was always my go-to. The nice thing about photoemission is there's a way in which we could directly look at band structure, electronic structure, correlated phenomena. It's essentially the benchmark in a lot of condensed matter physics and materials physics to basically validate our understandings of what's going on in materials. So in this case, I kind of viewed it as, let's do resonant photoemission, because resonant photoemission is basically where you do photoemission, but you do absorption at the same time. So you're in resonance with the edge you care about, and it means you have more sensitivity to the orbitals you care about. So if I take LMFP, this is where we know exactly where the ion redox is. And so that would be our model system for essentially validating this part of the calculations. And it should behave just as we expect. We should get most of our electron depopulation from the d electrons, and we should be able to account for everything we see in terms of simple electron counting of the d orbitals. So this is the electrochemistry. We did the absorption. The absorption gave us line shapes between the two endpoints. So we knew that we were fully oxidized, fully ion 3 plus by the point we measured, and we could simulate out the absorption both to show that it was 2 plus and 3 plus with a very ionic configuration of electron. Then we did photoemission and looked at the topmost states, and then we could, because we're on enhanced with the resonance, we could actually see the ion 3D state. You can see how it depopulates as we charge up. So all of that is behaving exactly like we'd expect for a battery cathode material. A lot of diagrams will show nickel in the same thing, where nickel oxides with nickel being at the top and than the oxygen 2p underneath. So we were like, okay, well, does that model still apply? So we take some really nice lithium nickel oxide cells that we made, nice hysteresis here. And then we looked at the valence band structure. And if I compare the charge and discharge state, the topmost, if I just do the top, look at the topmost occupied states, you can see there's a difference here where that is accounting for the electrons that we pulled out as part of the charging. So this is telling us where electrons from, but it's not telling us the orbital character because this is off resonance. But the reason we did that was to link it with different layers of calculations, and it kind of showed that this region would have a significant amount of oxygen character compared to D orbitals. A lot of D would be further down. So the calculations were in agreement that you're pulling out mainly from the oxygen sites, but we wanted to do a direct experiment. So that's why we did. So we charged it up. We saw that we were making unoccupied oxygen states. Then we looked at the nickel and we looked at the oxygen. So these bands here are basically giving contributions here. So you can see there's more weight here. With these signals, that's associated with there's more nickel content, nickel D orbital character, lower in the valence band. And then you can see that there's not so much change at the top of the nickel, but there's a big change with the oxygen. And that was directly showing that we're pulling electrons from more oxygen 2p-like orbitals than nickel 3d orbitals. So we are seeing a clear contrast from the case of LFP, lithium iron phosphate, and lithium manganese phosphate. We did more work, and I won't labor on too much on that, but essentially it's a little bit more complicated than just saying it's a ligand hole configuration instead of a D7 configuration. So you don't get good agreement if you do a D7 configuration. You have to account for the fact that there's actually more of a larger supercell structure to consider, where effectively average out as a D8L, where the L is ligand hole. But you can start reproducing really nicely with spectra if you do this well. And other groups have done this in condensed matter physics. And then we kind of compared all the different ones of lithium nickel oxide and the 811, so that model system we had. And the nice thing is you can actually see direct experimental bits of evidence that you have ligand holes. From the experiment, there's a signature of double ligand holes that you only see. So as you pull out lithium, you behave that out. So we tried to provide a bit of an infographic to contrast the difference with this associated with the publication. And so the idea is, I'm going to be as quick as, basically the quick answer with this is, can we get lessons from making new materials? And essentially one of the things we're saying is we're not got many, despite the lithium excess existing for since the early 2000s, we've not really been commercially adopted at scale. And that's because there's a lot of emphasis on mixing with the Li2 and Li3, which is probably not a good thing. You can actually see some interesting stuff with the lithium nickel oxide, and you can show that the same ligand hole theory works to that endpoint as well. So it should cover all the lithium excess systems. And other groups have now started to talk about using ligand hole theory to come up with new types of battery cathodes. So this is a way we can start exploring new candidates. So nice work from Stanford with Will Chu's group, where they did a really nice iron 3+ 5+ compound where they could show it was based on a ligand hole description where you didn't need to have oxygen dimers. And this would help explain old cathodes, not reconcile it with more established frameworks in condensed matter physics. Other people have started to use it, are pointing to like how this is also true for lithium cobalt oxide as well. So it covers a whole range of the layered oxides. As I said, it's a way to develop new lithium excess cathodes without the need to form dimers. So this allows us to start having different design rules to search new candidates that could replace these our existing battery materials. So if you want to learn more, here's some publications that you can. So this work we've directly seen with the resonant photoemission is now out in Nature Nanotechnology. This builds on the work which I mentioned with these two Joule papers, the ones where he used the 811 as a model system and evaluated the rigs in terms of defects, and then the other one where we sort of pointed to the calculations. And at that point, I want to thank all our collaborators across these times and people who have contributed, like Gallo, Zach and Matus, Ashok and Matt, but also the collaborations with Stan, Shirley, Claire, and Serena, and thank both funding from the US and the UK for this. So thank you very much for your attention.